All right, let's talk about the easy nomenclature and when it's going to be useful. You will see a good bit of this when you deal with alkene. So, many times cis-trans notation fails to determine what atom groups are on what side of the double bond. Okay, so recall from cis-trans, recall a structure such as this. We have carbon double bonded to carbon, a CH3 here, and H, CH3 here, and H. Recall that since we had two substituents, two equivalent atom groups on both the sp2 hybridized carbons, so we could compare this and this, or we could compare this and this. And since both of these, we have two groups that are equivalent, I can change it to this and make this a Cl. So just the CH3 groups are equivalent, and they're projected on the same side of the double bond. So we would call this a cis isomer. Okay. From that, we would call that a cis isomer. Since both CH3s are on the same side of the double bond, it is a cis isomer. Okay. Now, if we get to a structure such as this, where we have carbon doubly bonded to carbon, we have a Cl, we have a Br, we have a CH3, and we have a H. Well, if we draw a line that bisects that double bond, we see that on these two sp2 hybridized carbons, there is no atom or atom group that appears on the left or the right that's the same. I have a Cl here, a Br here, I have a CH3 here, and a H here. So I can't determine what's cis and trans from that. But there is a different notation that will allow me to prioritize according to atomic number, which is on the left and right, and determine what has priority. So this easy nomenclature, you are going to assign a priority, and that priority is going to be according to atomic number. Priority according or based on atomic number. And the priority we're assigning that's based on atomic number is whatever atom groups attached to the sp2 carbons. Okay, so if I do another example and I just say carbon doubly bonded to carbon, and now I'm going to say, well, this atom or atom group has priority 1, and this atom or atom group has priority 2 for that carbon. And I'm going to say this atom or atom group has priority 1, and this atom or atom group has priority 2 for that atom group. So 1 on this atom, the left, is projected that way. And on the right, 1 is projected that way. So this is opposite, okay? So if the high priority groups are on opposite sides, we're going to use a E notation, okay? Now, if my high priority groups were on the same side, I would use the Z notation. Okay, you'll see where I'm going with this. So if I go back to this example in green, okay, and I'm going to prioritize the atom or atom groups attached to each carbon. So on the left, Br has the highest atomic number, that would get 1, and this would be 2. And on the right, I'm going to prioritize what's attached to this carbon. So C has a higher atomic number than H, so this is going to get 1, and this H is going to get 2. All right, so since 1 and 2 are on opposite sides, this is projected that way, this is projected that way. Okay, this would be the E notation again. Okay, now, as stated, we're going to assign priority according to atomic number, and if the highest priorities on both sides of the carbons are projected the same in the opposite direction, it would be E notation. If it's projected in the same direction, it's going to be Z notation. So if we look at this, this is the same example that we did. And you see here that, again, priority 1, Br has the highest atomic number. It's projected that way. And CH3, we're just looking at the carbon compared to the hydrogen. It has the highest atomic number, and it's projected that way. So it has the designation of E. So this is 1 bromo, 1 chloro, propene. All right. Now, these can get a little bit more complicated. All right. So without naming, if we look at this structure, you want to draw your line as if you're bisecting that double bond, and you're going to recognize that this is the one of the sp2 hybridized carbons and the other sp2 hybridized carbons. Okay, so a third rule that we want to get to is just like when we did our S absolute configuration, we want to get to the point of difference. Okay, so if we get to a position that has the same atom, we want to see what's connected to that atom the same way we did in the absolute configuration determining R and S. Okay, so anytime you see a molecule like this, you can freely go ahead and write in what's attached to the sp2 hybridized carbons. Okay, so the point of difference is very important because you may look at a molecule and you say, well, it has the same atom attached. Well, I have to keep moving until I get to a point of difference that has different atoms attached that will allow me to assign priority 1. Okay, so let's look at this side of the double bond here. All right, in purple. Okay, so this carbon, this sp2 carbon, is attached to this carbon and it's attached to that carbon. So you would think that you're stuck, but I need to see what those two carbons are attached to. So this carbon, and we do the same thing the way we wrote out the attachments for the absolute configuration R and S. This carbon is actually attached to this carbon right here and these two hydrogen. So I have CH and H. Okay. Now this carbon, okay, this carbon is actually attached to this carbon. And because I have that double bond there, that says that I'm attached to two oxygens and this carbon. Okay, so I have OOC versus CHH. So that allows me to prioritize this group that's coming up like this as 1. And by default, this is going to get position 2. Okay. Now, on the other side of the double bond here in red, I need to prioritize what's coming off of this. So what's coming off of that sp2 carbon is going to be these two carbons in green. Okay. Now, for this carbon, what's attached? This carbon is attached to this carbon, and it's also attached to these two hydrogens. Okay. Now, what's attached to this carbon, which is actually these 3 hydrogen. So what that does, it allows me to assign 1 to this group and 2 to that group. So if I have 1 on this sp2 carbon and 2 here, and on the other sp2 carbon, I have 1 and 2. That says that my number 1 priorities, this is going that way, and this is going that way on that double bond. So that's opposite, and that's going to give me the E configuration. Okay. If we look at this second model, so we have carbon, carbon. We want to see what's attached to those sp2 carbons. Well, I have this carbon, which is attached to this carbon and 2 oxygens. Okay. Now I have this carbon here, which is attached to this carbon and 2 hydrogens. So C, it actually should be OCC, OOC. So OOC is going to beat out CHH. So this is why this gives priority 1. And by default, that's going to be 2. All right, so I prioritize this side. I prioritize the left side of the double bond. Now I need to prioritize the right side. Okay, so what's attached to this carbon is a carbon, and what's attached to this carbon is a carbon. So what I actually have here is C. That's going to be C bonded to a C, H, and a H. Okay. For this carbon, what I have is an H, an H, and an H. So CHH beats out HHH. So this is why this gets priority 1. So I see that priority 1 is going in this direction on that carbon, and priority 1 is going in that direction on that carbon. So that's going to give me the Z configuration. All right. Now you will have to take a minute and read what the text says and go through those examples in the book that are written out. Okay, we'll do several over this to make sure you kind of get the habit of what you're doing. Okay, so if I write this out in expanded, Lewis, and condensed, let's look at this structure. We have CH2, CH3, and hydrogen. Okay? So the first thing I want to do is I want to bisect and what I'm interested in is what's attached to that, and I can just write carbon 1 and carbon 2 if that helps you figure things out a little bit more clearly. So those are the 2 sp2 hybridized carbons in the double bond, and I want to prioritize what atoms or atom groups are attached to it. So I have my left and I have my right side. Okay, so I have a C versus a H. So this is going to get 1 and this is going to get 2. So for that first carbon in the double bond, I've already prioritized those 2. Okay, again, here I have a C compared to an H, and in the second carbon in that double bond, I prioritize that. Okay, so priority 1 on carbon 1 is going up. Priority 2 on carbon 2 is going up. Now, I don't want to confuse you by saying this is carbon 1 and this is carbon 2. I just did that for reference purposes. All right, now when we name, I'm going to put the numbering for naming in yellow. Okay, so when we name, we want the smallest number on the double bond. So this is 1, 2, 3, 4, 5. Okay, so our double bond occurs between 2 and 3. So this is going to be 2-pentene. Okay, now since we only have one double bond, we don't have to write the 2 with the E designation. Okay, so since both of these high priority substituents or atom groups are projected in the same direction, we can give this the Z notation. Okay, So this would be Z 2-pentene, or you can write Z pent 2-ene. Okay? So your EZ notation would give us this. Okay? And you may note that we do have the same, not to confuse you, but we do have two H's on both sp2 hybridized carbons, and they are both projected down, and that would give us the cis notation. So we could name this Z 2-pentene or cis 2-pentene. There are cases where cis trans is not reliable, and you will get an ambiguous notation. So Z does not always refer to cis, and E does not always refer to trans. Just keep that in mind, okay? Let's look at another example. Let's just write this out. All line angle, if you will. So let's say we have this, 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 and this. Okay? This is an alkene. This is an alkene that will have E or Z configuration. All right. This is a valid structure. This is something that you could see on the exam. So you want to apply the same methods. Okay. Now, it is perfectly okay to go ahead and write out your carbons and your hydrogens. You know this is a CH2. You know this is a CH3. You know this is a CH3. This is a CH2, CH2, CH3, CH2, CH3. I would expect you to write out that information if you cannot see it in your head, okay? So, I have a carbon here and a carbon here. So this carbon is attached to 3 H's, okay? And this carbon is attached to this carbon and the 2 hydrogens here. So CHH beats out HHH. So this group going down on that side of the double bond, we could say that will give us priority number 1. And by default, whatever is assigned 1, the other atom group attached to that sp2 carbon is going to be 2. All right. Now, we prioritize this carbon. We can move on to the other carbon on the other side of the double bond. We can move on to this carbon now, okay? So what's attached to this carbon is a C, which was this, and 2 H's. So what's attached to this carbon is a C, and 2 H's. Okay, So now I have to move on to this 2. So what I have attached here to this carbon is this C and these 2 H's. Okay? What's attached to this carbon is simply these 3 H's. We do this the same way that we did the absolute configuration of R and S. So you can easily see here that C HH beats out H H H. So this would get priority 1 and this would get priority 2. So for your left, number 1 is going in that projection. On your right, your priority 1 is going in that projection. So they are opposite, okay? So when we have opposites, that gets the E configuration. E configuration. Now, can we name this? Can we name this molecule? Well, why sure we can. So the same rules apply. We want to get the longest chain that goes through the double bond. So the longest chain that goes through the double bond is going to be this one. Okay? So our numbering for naming is going to be 1, 2, 3, 4, 5, 6, 7. Okay? So what we have is a double bond between 3 and 4. So that's going to give us 3 heptene. Okay? So I've circled my parent chain, and now we need to be concerned with the substituents coming off of the chain. So what's coming off of the chain is this group and that group, correct? So on carbon 3, I have a methyl. So I could say what, 3 methyl. On carbon 1, 2, 3, 4. On carbon 4, I have an ethyl. Okay, so we put these in alphabetical order like we did last time. We know the configuration is going to be E. And since we only have one double bond, we don't have to write the 3E. We can just say E. Some notations would write out the 3E. So we have E, 3, nope, E, 4 methyl, 4 ethyl, excuse me, alphabetical order, dash 3 methyl, dash 3 heptene. Okay, and you could also write that as E for ethyl, dash 3 methyl, hept 3 dash ENE. Okay. All right, let's look at an example that has 2 double bonds. 2 double bonds. We're moving on up to 2 double bonds. Let me see. Let's say 2. Let's say 2, 3, 4, 5, 6. And let me put a substituent here. And let me put a substituent here. And let's say we have a double bond there and a double bond there. So this is a good problem. This is a real good problem. So question marks about where to start numbering for naming. Let's see if I go from left to right. I go 1, 2, 3, 4, 5, 6. So what that does start me with the alkene on position 1 to 2. Okay. And it also gives me my substituent on carbon 1. Okay. Now if I go from right to left, that's 1, 2, 3, 4, 5, 6. So the black numbering puts my substituent on, it puts my alkene on carbon 2. My first alkene on carbon 2. So I want to use the red numbering, okay? I want to use the red numbering. So I have a total of 6 carbons. So those 6 carbons, and I have 2 double bonds. So I have a double bond starting on 1, and I have a double bond starting on 4. So I'm going to have 1, 4. I have 6 carbons. Hexadiene. 1, 4 hexadiene. And my substituents, I'm going to have 1, 5 dibromo. Okay. So that is the name without the EZ notation. Okay. Now, let's go ahead and fill in our implied hydrogen. We know this is a C and we have an H here. We know this is a C and we have an H here. Okay, so that's going to help us to assign priority. So I'm going to make this one red. And I'm going to make this one green. So on my red carbon, my red sp2 carbon, bromine is going to take position priority 1, hydrogen 2. Okay. It's the same thing. We're drawing this line down the middle. Okay. On my green carbon over here, this is going to be a carbon with 2 H's. So this carbon is going to take priority 1, and this hydrogen is going to take priority 2. Okay? So on the left, I have 1 going in that position. On the right, I have 1 going in that position. Okay, so for position 1, the priorities, that's 1 that way. So for position 1, which is this double bond here, across that double bond, my priorities are going in the opposite direction. So I'm going to have E to represent that first double bond. So I'm going to have 1E. Okay? Now, when I get to this double bond on 4, I put one in purple here and the other in red. Okay? Now, fill in your implied hydrogen. I would have a hydrogen going up like that. So when I prioritize, I'm going to come over here in this light blue, draw my line that bisects the double bond. So this carbon here would get position 1, this hydrogen would get position 2. Okay, on my red carbon, Br would get position 1, and this carbon, we know that's a CH3, it would get position 2. Okay, so I have to do this again, left, right. I mean, you don't have to write this out if you can see it, but I'm just doing this for demonstration purposes. So I have priority 1 going down, or on that side of the double bond, on the left side, which is the purple carbon, and on the red carbon over here, your priority 1 is going down again. Okay, so they are projected in the same direction. So for carbon 4 on the double bond, I would have Z. So the correct name for this with easy notation is going to be 1E for Z, 1,5 dibromo, 1,4 hexadiene. Okay. Now let's try another example with 2 bonds. So for every double bond, you potentially have the possibility of having an easy notation. There are cases when we talk about levels of substitution where you would not have easy notation. So let's try this molecule. Let's see, 2, 3, 4, 5, 6, 7, 8, 9. And let's make a double bond there. Give that a Cl, and let's come pretty close to it and make another Cl. Okay. Now, for numbering purposes, you can see we want to get to the direction that gives us the double bond first. Our first double bond, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have a diene again. So we have 3, 5 nonadiene. Okay, so 3 represents the start of this first double bond on 3. 5 represents the start of the first double bond on 5. Now we need to take care of the business of the substituents. I have a 3, a 3, 6 dichloro. Okay, that's 3, 6 dichloro, 3, 5 nonadiene. Okay, And the last part is to determine if this is E or Z on both double bonds. So go ahead and put in your implied hydrogens. Make that a hydrogen there, and we know we have a hydrogen here. Okay, let's bisect the double bond. Okay, we know that this is a carbon, we know this is a carbon, we know this is a carbon, we know this is a carbon. Okay, now let's prioritize. So we have a Cl versus a C. So this is going to be 1, and this group here going down is going to be 2. Okay, on this side of the double bond, we have a C versus a H. So this is going to be 1, and this is going to be 2. So for position 3, we have 3Z, because both the left and the right, they're projected in the same direction. Priority ones are projected on the same side of the double bonds. Okay, now let's take care of the order of 5. So 5, I've already done this one. Now on carbon 6, I have a Cl projected down. That's going to take priority 1 versus a C. That's going to be priority 2. This is a C with 2 H's. So the Cl beats out the C that's going up in that direction. Okay. So let me erase that. And in blue, I have to take care of these two. So I erase that for 4, so I can take care of 5. So I have a C that's going down, that's going to get position 1, and a H that's going to get priority 2. So for 5 and 6, I have both priority 1s going down. So they are projected in the same side of the double bond, so that's going to be Z again. So that's going to give me 5 Z. So the correct name is 3Z, 5Z, 3,6-dichloro, 3,5-nonadiene. Okay? All right, let's look at another example. These get to be quite interesting and fun, as you can see. If I draw this molecule, and let's put some double bonds in to make it interesting. Well, what is this? Well, let's start numbering. We want the lowest number for our first double bond is 1, 2, 3, 4, 5, 6, 7. Okay, so we have 2 double bonds. We know we're going to have a diene. So this is a hepta. Diene. Okay. Now, where are the double bonds? I have one starting at 2, and I have one starting at 4. Okay? Now, is this E or Z on positions 2, 3, 4, 5? Well, let's draw in our implied hydrogen. Let's put a H there, and we know we have an H there. We know we have an H here, and we know we have an H here. That completes our octet for each carbon. We know these are carbons. Okay? Now, let's bisect that double bond. So we're going to compare this side, which has a carbon and a hydrogen. So that's going to get position 1. That's position 2. Okay? We're going to compare this side. This is going to give us another carbon and hydrogen. That is going to be position 1. This is going to be position 2. So I have established the conformation or configuration of the double bond to 3, and that's going to be 2. They're both priorities are projected on the same direction, going that way. So that's going to be 2Z. Okay. Now I have to take care of the business of 4 and 5. So I need to erase this temporarily so I can denote 4 and 5. Okay. So for position 4, I have a C going down versus a H going up. So that C here is going to give me priority 1. The H is going to give me priority 2. And again, I have the same thing. Attached to this carbon is a carbon going in this direction. I can say down. And this hydrogen is going to be priority 2. So both priority 1s are projected on the same side of the double bond. Just keep in mind that this is flat. If I stand this molecule up, then it would be going down. But they are on the same side of the double bond. So that's going to give me 4Z. So the correct name for this is 2Z, 4Z, 2,4-heptadiene. And for those who are wondering, I can name this hepta, guess what, dash 2, 4 diene. Both of these names are synonymous. They mean the same thing. Please get familiar with both of them. Okay. Now, let's try a molecule, and I'm going to put in some different functional groups. So naming is not important. Naming would not be important. What would be important is to determine what is E or Z across the double bond. So let's look at this, for instance. Let's look at this. Okay. And yeah, we can put in a triple bond. And on this side, we'll look at this. And let's make that a double bond, O and an H. Okay, so just go ahead and write in what you already know. This is a carbon, this is a CH3, this is CH2, this is a CH2, this is CH3, this is a carbon, this is a CH3, this is a CH2, this is a carbon, and that's a hydrogen double bonded And this carbon is also double bonded to an oxygen. So what we want to determine, let me change this to a CA. Let me change that to a CL to make it simpler. What we want to determine is what's going to be the configuration, E or Z across this double bond. Well, by making that a CL, it makes it easier a little bit. The outcome still would have been the same for CH3, but Cl is going to take priority over this carbon. So we have Cl projected, priority 1 projected in that direction. Now, when we come over here to this other sp2 hybridized carbon in green, it's not absolutely clear as to what the priority is. Okay, let's examine. This carbon is attached to this carbon and this carbon. Okay, now the same rules apply. The same rules apply with the absolute configuration. This carbon, since it's triply bonded, that means it's bonded to a carbon, carbon, and another carbon. Okay? Now, this carbon, it's bonded to this carbon, and the two hydrogens. Okay? That carbon is bonded to where I get this C from. Where I get this C from, I'm referring to this as that C. Where do I get these two H's from? I'm referring to this H and that as another H. Okay? So, as we can see, CCC beats out CHH. So, this would take priority 1 and this would take priority 2. So priority 1 is projected in that direction, and since this is in that direction and that is on that direction, this would be the Z conformation. Okay? All right, how about another one? Let's say we have this double bond and this, and then we have this, and we're going to put a nitrogen here this time. And then we have this, and then we have this. Okay? So let's write out what you already recognize. This is going to be a CH3. We know this is a carbon, this is a carbon, this is a carbon, this is a carbon, and that's a carbon. Okay? So on this side of the double bond, this carbon is going to take priority over this hydrogen. So this is 1. By default, this gets position 2. Okay? Now, here we have an interesting situation. We have a carbon here, and we have a carbon here. So this carbon is triply bonded to 3 nitrogens. So that's going to be N, N, N. I'm referring to this carbon, okay? Now, this carbon, which is here, it's triply bonded to a carbon, so it's going to be C, C, C. Now, nitrogen has an atomic number of 7, which is greater than carbon's atomic number of 6. So 3 N's beat out 3 C's. So this is going to get position 1. This is going to get position 2. So I have 1 going in this direction for this carbon, the left, and I have 1 going in that direction for the right. So since they priorities are going in opposite directions, I'm going to give that the E designation. Okay. Now, this can get pretty deep. For the most part, these examples would be something similar that you would see on the exam. You have to know how to find the first point of difference. If you are confronted with an sp2 carbon that has the same atom bound to it, that means we need to see what that atom is attached to. So as I said, it works the same as you did with the absolute configuration of R and S when determining the point of differences. Okay? So practice this, and on the next session, we will visit a new topic that pertains to alkenes.